Hey there guys, welcome back to a brand new video. Today we are moving on from basic partial derivatives and we are going to be moving on to the idea of tangent planes and tangent vectors. So we are going to begin this video with a proof. If you'd like to skip the proof, you can go ahead and skip to a time mark that I'll post in the description or bring up right now when I'm editing the video. It's important to know this definition and it's important to know the understanding. If you can find a better description of this identification and the proof, then go ahead, watch that instead and just use that later on if you'd like to. So let's go ahead and let's start with a basic geometric proof. So back in one-dimensional calculus, we looked at the tangent line, and that was only consulting a one-direction change, the x and the y. So we were looking at the change of y in terms of x. So that was our change. In this part, we are looking at z changing in x and y. So we have two components that we have to deal with. So it's going to be a bit trickier, but not too bad to derive here. So let's say we have a continuous function z is equal to a function of x and y. This could be anything like something like z is equal to x squared plus y squared. You can find the tangent plane for that. You could use this formula for a continuous part of an uncontinuous function. And when I say that is that particular part you're looking at has to be continuous about a bound. Okay, so let's just consider an absolutely continuous function. Let's just draw some random function here, a surface you could say. And let's call this z is equal to f of xy. Oh, not x naught. Getting ahead of myself there. F xy. Okay, now let's draw a pair of axes on here. Three-dimensional axes. Got the z, the y, and the x. X, y, z. So this way is the z, that's the y, that's the x. Now, we need to have a given point to find the tangent plane. So let's say u is our given point. X naught, y naught. So just a particular point. And that is going to be, let's say, this height, for example. That would be our height. And let's define x naught, y naught as about here. So we're translating to about here. That is our height, and we shift our coordinate system up to that height to find the tangent plane there. So, okay. Let's define it. So our constraint height is given by f of x naught. And we can allow this to equal z naught, which is just, again, our given height. Our given height of our surface. This is a pretty basic thing that we use even in terms of the one dimension when we're looking for a tangent line. And now let's have a think of how we can define the change of the y and the x to find a tangent plane formula. So in level 2 and even 3 in CA, we looked at tangent lines, and even into university, we knew that y minus y1, y naught, was equal to mx take away x naught. So this was our gradient in terms of x. M was equal to f prime of x at that particular point. We're going to use something very similar here. We're going to constrain ourselves to a level curve. Now, level curves are just basically little functions that run right through the surface. It's like, you could think of it as a geological map if you really wanted to, a crack running through the ground. That would technically be a surface curve, believe it or not. So we have this surface curve, and that is in the direction of y in this instance. We also have surface curves traveling in towards x, the x direction. So let's constrain ourselves to the y direction at the moment. And if we're constraining ourselves to the y direction, that means we are going to hold x constant. Is that right? Yes. And what do we do with that? Well, that means we can take the partial derivative in terms of y. So we get f of y is of x naught, y naught is equal to the partial of f in terms of the partial of y at the point x naught, y naught. Okay? And just like the idea of the tangent line, we need to look at the idea of finding a tangent line on the level curve for z in the direction of y. Well, we know a definition for a tangent line, don't we? We know that the given line is something like z is equal to z naught of shift of height, which makes sense, plus f of y, x naught, y naught, multiplied by y minus y naught. Okay, so we've got a tangent line in a potential direction, so that makes sense, right? Yes, it does. And if we know that that is the situation for the y direction, does that mean it is the same for the x direction? The answer is yes. So we can go ahead and make another tangent line in the x direction, and we get f of x, x naught, y naught, multiplied by x, take away x naught, and that is our different, and plus the height. And now we need to somehow combine these all together to create the identification for the tangent plane. And all you'd have to do really is sum all these. Now note that these aren't actually the same. That was a mistake. That should be Z1, that should be Z2, because they run against different heights. So now we have found the tangent lines in the particular direction of y and x. We can combine these both to find the tangent plane. So how do we go about doing this? We've got two constants, and I can say that we don't need both these constants because technically they are both z naughts. So z1 and z2 are z naughts. And what that means is they occur at the same level, the same base level. So let's look back at our diagram. We were taking the tangent line at this particular point in those particular directions. They both intersect with one another. That's what it's stating. So how can we go ahead and simplify this down? Well, if we have this as a true statement, then all we have to do is take a linear combination of this part, and this part. And that would be our equation for the tangent plane. So let's go ahead and find our definition. Z is equal to Z naught plus f of x, x naught, y naught, multiplied by x, subtract x naught, plus fy, x naught, y naught, multiplied by y, take away y naught. That is our definition that we use in class, in other concepts as well, but there are also other ways we can look at finding this definition, and one possible way is using vector geometry. And the idea is we have a point on our function. We have a point on our function f of x naught, which we looked at before as well, and we called that z naught. So we start at this point, and then we have two directional vectors. Two vectors going in two different directions perpendicular to one another. So how can we define the vectors that define that direction? Well, it makes sense that it would involve an x component, 0, and its derivative, and the y component for the second one, 0, 0, a y, and then a change in the y direction. Just trying to think of it geometrically. So a change in the y, which would be f of y, x naught, y naught, and f of x, x naught, y naught for this direction. And because we're only in the x direction, that defines our vector as 1, 0, f of x, x naught, y naught, because that is describing our change of z, or f in this case. And in the case of this, we are looking in the change of z in the y direction. So that would mean that would have 0, 1, and f of y, x naught, y naught. Technically that's z prime naught. So that is the same as 0, 1, z prime naught. But we'll just leave it as this here. So what would this mean? Well, that would mean, by definition, we have our point defined x naught, y naught, and f of x naught, y naught. And then we have some scalar multiplied by 1, 0, and the change of x, x naught, y naught, and then we add by another scalar 0, 1, f, y, x naught, y naught. And if you're to allow these to equal one another, so z to equal that stuff, and x to equal that stuff, and y to equal that stuff, you'd actually end up finding the equation of the tangent plane through this method, which we will continue doing in a later stage where we look at vector geometry. Alright, so now we can go ahead and find the tangent plane using the tangent plane equation that we found earlier. So the tangent plane was equal to z, take away z naught, is equal to f of x, x naught, y naught, x, take away x naught, plus in the y direction at x naught, y naught, multiplied by y, take away y naught. A bit messy there, ran out of room there. And hence we get z, take away 2, is equal to the derivative at x naught, y naught, in this case 1, 2, in the x direction, 2, multiplied by x, take away 1, plus 1, y, minus 2. Just fix that y up. Y minus 2. So we get z is equal to 2 plus 2x minus 2 by expanding here, plus y minus 2. We get some simplification here. 2 cancels out with this 2. And henceforth we get z is equal to 2x plus y minus 2. And that is our tangent plane.